Hello everyone, welcome to our data structures and algorithms concept series. In this video, we will cover about the linked list data structure. We'll understand what is linked list using a real life example, different types of linked list, the memory representation of the linked list, and what is the impact on each data operation when we use the linked list data structure, and also different use cases of the linked list. So that we'll get an idea about, depending on the problem, whether we should use the linked list or not to solve that problem very efficiently. So let's start. Let's understand the linked list using a real life example. Whenever we go for a traveling, right, we create a playlist with our favorite songs and we keep adding new songs to it, or if any song which we don't want to listen, we remove those songs from the playlist, right? So you can see how efficiently we can insert or remove the songs from our playlist, and this represents the property of the linked list, right? And each song is connected to its next song. Like basically one element is connected to next element, another element, right? So it's basically represents the linked list, and it is a linear data structure, as you can see, right? One element is connected to only one element, right? And the elements are not stored in contiguous memory location. We will understand this in the next slide. So this is the main difference between the linked list and array. In our previous video, we saw that array, it is stored in a contiguous memory location and how its memory representation is. In this video, we will understand about the linked list, how the memory location are basically represented. We'll understand the memory representation of linked list in next slides. Element in the list is referred as a node. So whatever you are seeing, song 1 or song 2, right, it is called as a node, which stores the actual data, basically our song, and pointed to the memory location of next node. Basically song 1 node containing the pointer to the memory location of song 2, right, in the list, right? It allows the insertion and deletion without shifting the elements. So when we try to insert or delete elements from array, we have to shift to fill that gap. But in linked list, we don't need to, right? We'll understand that in the next slides. But these are the properties of the linked list data structure. So linked list contains two types of pointer. One is the head pointer, which points to the first node of the linked list, and another is a tail pointer, which points to the end of the linked list, right? Tail pointer is maintained in most of the programming languages, but in some of the programming languages it is not present. The reason why most of the programming languages are also maintaining the tail pointer, because it gives some performance benefits for insertion. We'll understand that in the next slides, right? What is node, right? Node represents the object, basically where you can keep your data, which is here it is integer, it can be string, char, or whatever it is, right? And the pointer to the next element, basically it contains the reference of next element. In most of the programming languages, it is an object, but in a C, it can be represented using a struct, right? So it is just a term which it's a term basically used to represent the element in the linked list, right? Like for example, in this list, you can see that the highlighted ones are representing the node, right? The object which holds the data and pointer to memory location of next element. So for example, here, if we go into a little bit more detail, here 5 is your actual data, and next part is basically the pointer to the next element, basically the reference of 7, right? So let's understand the linked list memory representation. Let's assume that our memory is represented like this as a grid to easily understand the memory representation. So green one is a free memory blocks, and black one are used memory blocks, right? So when you declare like this linked list, let's say integer, you can have char, string, whatever it is, list equal to new linked list int, right? So it basically what it creates, it creates the object for the list and linked list, which contains basically your head node and tail node, because as I mentioned, list maintains these two pointers, head for beginning and tail for end, and int count, depending on to the different programming language, it can contain more as well, but the more important is head and tail, right? So once we create this, then the node is basically what we saw in the previous slide. It's the object which contains your actual data and the pointer to the next node, right?
Once we do this, it creates a list object, and reference is basically stored into this variable list, right? So we have not created any node. There is no memory allocated yet. Only the memory is allocated for this object to contain this. Uh, it will contain initially the null value, head and tail, right? So when we add any element to it, right, to the end of the list. So basically, we added 5 here. It created a node. So yellow one here represents the node object. So what happens when we add 5? Then the head and tail pointer of the linked list object will point to 5, right? And you can see it is not contiguous. It is created anywhere where is the free memory is available, right? And then when we add 7 element, again you can see it is created. The memory is allocated from anywhere where is it, the free memory is available, right? It is not contiguous like array. So like from list, the head is 5 now, and next of 5 is the 7 node, and the linked list tail is at a 7, right? Now, if we add an element at the beginning, add first, right? 11 if we add. So you can see the memory got allocated for 11 node. Then the head will point to the 11 because we added to the first, right? And then 11 will point to the 5, and 5 will point to 7. So this is like 11, 5, 7 list, and the tail pointer will be at the 7 only, right? So we saw how the memory representation of linked list looks like. Whenever the node is actually created, then only the memory gets allocated, and it can be allocated anywhere and not contiguously, right? So that allows linked list to grow dynamically. We don't need to worry about the size of the linked list, right? As long as we are not violating any like basically memory consumption and all those things, right? There are 3 types of linked list. One is singly linked list, doubly linked list, and last is a circular linked list. We'll understand singly linked list and doubly linked list in much detail. Circular linked list is nothing but just an extension, and both singly and doubly can be represented as circular linked list. We'll understand going further. So singly linked list. So if you see here, this linked list represents the singly linked list. What does that mean? That it maintains the 2 pointers, head and tail. Head is the start of the list and tail is the end of the list. You can see this is the starting point, this is the end point. And each node maintains 1 pointer next, which points to the next node. So whatever the arrow you are seeing from left to right, it is the next pointer. 5 is next, pointing to reference of 7. 7's next is pointing to reference of 9. And because it is at the end, the reference of next element, next pointer is pointing to null, right? That's how we come to know this is end, right? It allows only one-way traversal, because if you see arrow direction is like this, so you can traverse from head to tail only, right? Now insert at the end and beginning, right? So initially, let's say head and tail are pointing to null, and when we want to insert 7, it created one node with the data 7, and next pointer is null because it is the first element in the list. Head and tail will point to that first node now, and let's say if we try to insert the 5 at the beginning, right? It can be easily done by just creating a 5 as a node object, and just point that next reference of 5 to the 7, right? And then shift the head to 5. Now we added the element at the beginning of the linked list, right? Similarly, let's say if you want to insert 9 at the end, uh, like this is our current linked list after adding 5. So when we create a new object of node with data 9, then we point the tail pointers next. The tail pointers next, tail pointer is pointing to 7. The next of 7 will now become 9, and the tail pointer will shift to the 9, right? So inserting at the end and beginning is very fast, right? Because we are maintaining the head and tail here. That is the reason why most of the programming languages also maintain tail, because it allows the insert at end very efficiently, right? Now insert any other place apart from beginning and end. Now, if this is our linked list. Now, if we want to insert 8 between 7 and 9, we'll create the 8 node, the node with the data 8, and its next will pointing to null. Now we want to insert that into this list. So what we will have to do, that we'll have to create a temp pointer, which will see whether where to put, like so it will go to 7. Okay, we have to insert it after 7. So what it will do, the temp 7 of next will now point to 8, and 8 of next will point to 9. So using that temp variable, we can insert at 8 between 7 and 9. Now you can see we have to traverse the list for inserting in middle or at any other place apart from beginning or end, right? Delete from beginning. So if you see, delete from beginning is easy because we are maintaining the head pointer. So we just have to shift the head pointer to the next node of the current head and delete the head node, right? And while before deleting, we need to set, in some of the programming languages, we need to set the next of that the node which is getting deleted to null, so that it can be collected by the in a garbage collection, or the memory can be freed. Delete from any other place apart from beginning. Delete 9. So let's say if we delete 9 here, you can see that we have to traverse till one node before 9, and once we traverse, then we just need to delete this. How? So next of 7 will now point to null, and this node will be freed, and tail will come to the 7 now, right? So we brought the tail to point to at the 10th location, and then delete 9, and then make next of 7 as null, basically representing end of the list, right? So delete also, when we want to delete from middle, we have to traverse using some 10 pointer. So this is one more thing to note. Now coming to the doubly linked list, right? It also maintains the 2 pointers, head and tail. Head for start and tail for end of the list. Each node maintains now 2 pointers. In a singly linked list, it was only 1 pointer, which was next, but in this, it maintains the 2 pointers. One is next and one is previous. Previous points to the previous node, and next points to the next node, right? So for example, like this, now 5's previous is null because there is no node here. It is head node. Next is 7, and 7's previous is 5. 7's next is 9, 9's previous is 7, and next of 9 is null, right? So you can see it allows the traversal from both the ends, right? From head to tail using next, and from tail to end using previous, right? So we can traverse from using this next pointer from head beginning to end, and for using previous pointer also from end to beginning, right? So this is the advantage doubly linked list gives, like apart from basically it provides you the traversal from both the ends using previous and next, right? So let's say insert at the beginning. Let's say we are pointing to null before, and we want to insert 5. It creates a new node with previous and next as null, and then points head and tail to that node. Now, if you want to insert 7 at the beginning, it will create a node with the 7, next and the previous null. And then what it will do, it will point the new nodes next to 5 and our heads previous to the new node, right? And then it will shift the head to new node, right? Now inserting at the end. So if we want to insert at the end, let's say we have one node here and we want to insert 7 at the end. We create the node 7 with previous and next as null. And you can see that we connect the previous of the new node to our tail, and next is null, and the what are the next of tails should be pointing to the new node, right? And then we shift the tail pointer to the new node, right? Now, if you want to insert at any other place apart from beginning, like similar to singly linked list, we have to also maintain 10 pointer here. Like if you want to insert 8 between 7 and 9, so we need to travel till the point where we need to add. Now we came to 7. Now we want to add 8 between 7 and 9. So what we'll do, we'll point next of 7 to the 8, and previous of 8 to 7, next of 8 to 9, and previous of 9 to 8, right? And it will change our doubly linked list like this, right? So here also, for inserting at any other place, we have to traverse in the doubly linked list, right? Delete from beginning, because we have a head pointer, so we can shift the head pointer and then delete that previous head and then make the previous of new head as a null, right? uh, Delete from any other place apart from beginning, like similar to the singly linked list, we have to traverse. Basically, now if you want to delete 7, we maintain the temp pointer, and now we want to delete 7. So the current temp, we have to point that next of temp to the node which we are deleting. The next of that node we need to point, like 5 we need to point to, next of 5 need to point to 9, and 9 of previous needs to point to 5, right? So that's how we can remove the 7. You can see like this, right? And then the 7 node which is now detached will get freedom, right? So for the deleting from any other place, we have to traverse till that point, right? Now circular linked list is basically the difference only is that all nodes connected to in a such way that it forms a circle, right? And it is done by connecting tail node to head node instead of pointing to null. Previously, tail was pointing to null, but the next of tail is now made to point to head. This is a circular singly linked list. And in a circular doubly linked list, the next of tail element is pointed to head, and previous of head is pointed to tail, right? Previously, the previous of head was null and next of tail was null, right? But they are connected like this, like previous of head is connected to tail and next of tail is connected to head, right? This is called as a circular doubly linked list, and all the insert delete operations are same as singly and doubly linked list, right? Only thing we need to maintain is pointing from tail to end. That pointer we need to maintain, right? Let's understand the performance of different data operations for all types of linked list. If you want to insert at the end or beginning, then we have a head pointer for beginning and a tail pointer for end. So we can immediately insert. That is why it is O of 1 for all types of list. If you need to insert at any other place, we need to traverse till that point and then only we can insert. If you want to insert at any other place apart from end and beginning, so it will be O of n in a worst case. N is a number of items in a linked list. Delete at the end or beginning, again because of head and tail pointer, we can efficiently delete at the end and beginning, use O of 1 complexity. And similar to insert, deleting any item from other places apart from end or beginning, we need to traverse till that item or node. In a worst case, it can be O of n, right? Search an item, we need to search each and every node to see whether it is matching with our item which we want to search. So in worst case, we might end up traversing whole list, which is O of n. And if you want to access item randomly, linked list does not provide indexing mechanism. So we need to go till that position. If you want to access fifth element, we need to traverse till fifth element and then get the item. So in worst case, it is O of n. So different real life examples uses a linked list based on the use cases they have and which linked list supports. For example, the use case where we want to frequently insert or delete without incurring the cost of shifting elements. So linked list handles this capability or use case very efficiently. So that is why different real life examples like music playlist where songs are added or removed very frequently, or LRU caching where operating system inserts or removes the caching item from this LRU based on their uses. Linked list can be efficiently used here to handle this examples, right? The next, if there is a use case where we need to have a mechanism to flexibly grow and shrink dynamically without wasting memory, right? Then linked list can like supports this use case. So that is why it can be used in some of the examples like where graph data structure representing the connections there. We'll understand how linked list is used in graph data structure in upcoming videos. And operating system memory management, where memory allocators maintains the free block memories using linked list efficiently and allocate the memory when required, or insert the free block memory in that linked list whenever some memory block are freed, etc. Right? So depending on different use cases, which linked list can support, different real life examples uses the linked list. So we understood about the linked list data structure, its memory representation, different types of linked list, and then we understood its impact on the different data operations when we use the linked list and use cases. So based on this, we'll at least get an idea, depending on the different problem statement, whether we should use the linked list data structure or not, depending on what use case of that problem, so that the algorithm can work efficiently. So hope you understood the explanation. Thank you.
Hope you understood the explanation and understood about the linked list data structure, got the idea about different types of linked list, the use cases of the linked list, the memory representation, and how is the performance of each data operation when we use the linked list, so that it will help us to think in a right direction whether to use linked list or not, depending on the different problem statement. If you like the video, please share and subscribe. Thank you.